There you go.
Huh. Did I do a problem like this before, I wonder? If I did, I forget. Oh wait, this is U sub. Yeah, the U sub thing. Wait, this doesn't help though. Yeah, this doesn't help at all. I don't know.
Let's work on that one. Not too bad. Just make sure you know the idea of a substitution.
Is it easy? I don't know. Is it like... Yeah, I don't know about this one.
Well, I hope for you in this case that the U is fairly obvious in this one. The U
Okay, so there is a U.
is the only thing there. The only thing I wanted to make sure you see here is, do you take the exponent when you're picking a U? Do you ever take the exponent with it? No, because the derivative.
Alright, let me... Let's do the full thing then. Oh wait. Oh, this one is easy.
It has to be there, right? So if I took a derivative of that, it's 15, 2x minus, that's not going to appear again in our integral. That's not going to work out for us. So it's almost exclusively the inside of something that you pick for your u, and that works like 90% of the time. By the way, this substitution method sometimes makes integrals go really, really fast. Have you found that out too? So it's kind of nice. If you can find the right substitution, that's the hardest part, then it works itself out. Last thing we'll do, if you don't want to put a plus c right here, that's fine. Just make sure it's at the very end of your problem. You have to have a plus c. But make sure you have substitute back in for x. I get a lot of people make it down this far, which is technically correct, but it's also it's also incorrect because we want this in terms of x, not in terms of u. So if you didn't make it down that far, just do your substitution. And that's what we should get. How many people were able to make it down that far on their own? Good, that's all about everybody. That's fantastic. All right. Now, if this is new to you, then of course this is going to take you some time to figure out. Now, the last one, before we go on to some a little bit more advanced idea up here. The last one, I think I showed you the first step here last time. I said that don't let the integral really confuse you into making.
Alright, so you can split this one up. Probably gonna substitute this part right here. This one is easy. Now what is secant squared on the trig thing? Is it on the other one? Secant squared. Wait, that has to be split up, doesn't it? 1 plus tan squared. Okay, how does that help though? Alright, I don't know from here.
And you think it's something harder than it is. Namely, if I were to look at that integral right now and try to pick a substitution, there is not a good substitution for that right now. Because if I pick that as my u, I'm still going to have an x in there, right? So I'd have a du something, and I'd have an x, and that's not going to work out for you. You can't do a direct substitution on that integral the way it is right here. But what you can do is use some of the principles of integrals. They're basically the same as derivatives. It says you can pull constants outside of your integral if they're being multiplied by some function of x. It says you can split up the integral or derivative by addition and subtraction. Not multiplication, but definitely addition and subtraction. So what this says is this is really not one giant integral. It's actually two separate integrals if you want to think about it that way. So the first thing I do in some of these integrals, if they look too daunting, you're like, oh my gosh, I don't even know where to begin. See if there's a plus and a minus. If there is, sometimes you're able to separate those, and sometimes it makes it easier. And I know I did show this to you last time, but this you can look at as 1 over x squared dx. Don't forget the dx. And secant squared of pi x. Don't forget the dx. Now, can you do this one? What would be the first step on doing that one, by the way? Very good, because it's got to fit your table, right? There's no substitution needed. You don't need that. But you know how to do this one already. We practiced that. How about this one? Is there a substitution necessary for this one? Yeah, there is, because that's not just an x. That's a pi x. What I'd like you to do is figure that out. Okay, go ahead and do both integrals. This one's kind of a basic one. This one's going to require a substitution for you. So what do you do with these things when it's plus and minus? Well, you're supposed to break up first. Which is also what you're supposed to do with your girlfriend right before Valentine's Day, just so you know. That way you don't have to buy presents. It's a bogus holiday anyway. If you time it right and you break up right before Valentine's and right before her birthday and right before Christmas and get back with her, it's awesome. You save so much money. Just kidding. I've never personally done that. I know someone who has done to, but.
She actually fell in the trap 3 times.
I'll tell you the story later. Okay, so your u should be pi x. Remember, it's the inside of something. If you're having trouble looking for a u, or finding a u, and there's something in parentheses, try it. What's it hurt? I mean, it takes 5 seconds to figure out you're wrong, right? That's all it takes. So if you're having trouble, just pick something. And if you're wrong, you're wrong. Who cares? Just go back and redo it later, pick something else. There's only a finite number of selections you can make in an integral. So if you try something and you're right, great. If you try something you're wrong, just pick something else. Don't give up. Du in this case is pi dx. So du, oh, remember pi is a constant, right? So if it was 3x, it'd be 3. Now it's not 3x, it's 3.141592, whatever, forever, but it's pi. So du over pi equals dx. And now we can go ahead and make our substitution, and it only affects this second integral because I have two distinct integrals now, which is great, and that's what we want. So here we're going to have integral of the secant squared does not change, only the angle changes. Remember, this is not being multiplied either. That is not a multiplication, that's secant of, not times. That's your angle. You can't manipulate that in any other way besides the substitution. That's going to be a u. And then du over pi. How many people made the substitution looks just like that? Good, that's fantastic. That's the correct substitution. Now, this integral is pretty easy. We're going to do x to the negative 3 over negative 3, right? What did I do wrong? It's a very common mistake.
I have to add 1.
Yeah, and some people go, oh, well, you're adding 2 plus 1 is 3. Well, you have negatives here, so it's kind of flipped on you. Negative 1 over negative 1. Don't add a plus c yet, that's fine. We can add a plus c at the very end of our problem. If you add it now, it might get a little confusing for you. Then a plus sign because we have a plus sign. I know the integral of secant squared u is good because the derivative of tangent is secant squared. That's why that works. Remember, we're just going opposite of a derivative now.
Was that on my table? Oh, how did I not see that? Okay, so this can go away.
Not tangent squared either, it's just tangent u. What happens to that pi?
Becomes 1 over pi.
I guess I'll show you that step, huh? The over...
Oh, I didn't put it over 1.
Pi, you can make that 1 over pi, and then secant squared u du. If you'd like to show that, that's probably the appropriate way to write it. Show your constants pulling out, it's on a denominator, it stays on a denominator, and then go for it. We already talked, this is tangent u. Have a plus c here or not, you just need 1 plus c at the very end of our problem. We'll probably make things a little bit prettier, and what I mean by that is we'll drop down our negative exponent. This will be negative 1 over x. This will be plus tangent, well, tangent of u. Now our u is listed right up here, we just have to put it back in its place. You can have 1 over pi if you'd like, or you can have the whole thing over pi if you'd like. It doesn't really matter. One thing I do have to make certain that you do know, do those pies cross out? No. Heavens no. OMG, that earns you a big fat circle no with like 10 exclamation points and then I burn your paper in front of you, right? That's what that earns you. No, you can't, because like I said, that's not multiplication, that's an angle. This is division. You cannot cross that. There's no trig rule that says you can. What you do need to do is put a plus c. How many people feel okay with that example? Good, so looks difficult? Sure. Is it really? No, not really. Is this one? Not really, as long as you know the correct substitution. That's what this whole process is about, and that's why I'm giving you so many examples, so you kind of see some different instances of what you can do, what you can't do, and some substitutions. You ready to tackle this problem then?
Go plus C.
Okay. Now,
Can't see, whatever. Okay. So. Seeing like sine x over cos x. Times 1 over, or no, times sine x. So tan x, sine x, dx. And then did that help? Maybe not. Well, sine squared x equals 1 plus cos squared x, right? I think. No, 1 minus cos squared x. I don't know about this either. Interesting. No, I'm not seeing anything. Maybe 1 over secant x? I don't know, I'm just gonna watch.
Is that in your integration table? No. Sine is, cosine is, but not sine squared cosine. Well, here's the deal. If we're talking about using a substitution to solve this, well, what would a good substitution be? Because here's the deal. If I pick cosine, the derivative of cosine is negative sine, right? Well, that's up there. If I pick sine, the derivative of sine is cosine. Well, that's up there. So which is the correct choice? And the answer is the one that takes care of all the other x's. So for instance, if I picked, let me show you how you'd find out you're wrong on substitution in about 5 seconds. You ready? Here's how you find out you're wrong. You pick your u, you take your derivative, maybe 15 seconds, I don't know. You solve for dx, and you do your substitution, and it comes out with something that doesn't work for you. For instance, this is still sine squared x, right? The cosine was u, and dx is du over negative sine x. Now, one thing that's great about this is gone, but only one of those is gone. Did I get rid of all the x's? And there's nothing else you can do there. If you didn't work out...
Let's try the other one. This doesn't help either.
out kind of nicely for you. Either there's another substitution you have to make, or you made the wrong substitution. And that's most of the time in this class, that's most of the time what happens. All right, so for us, we go, oh man, this didn't work for us. I better not try to like force this through. It's kind of like, oh my gosh, I almost made a Star Wars analogy.
Totally should.
Yeah, well, anyway. You have to let the force flow. You can't force this thing, or it doesn't work. It doesn't work. You can't make it happen. You gotta just let it work for you. Yeah, it's not that much work. So anyway, how do we find sine or the correct u to begin with? Well, think about it. What's sine squared x mean? Sine x little 2, right? It's actually inside of parentheses with an exponent, and that's the correct substitution. So this really means this.
I think I got it.
Now, of course, if I wrote it like that, it's a little bit easier to see. Now, I'm not going to write it like that because we typically will write trig functions with the sine squared, but you need to know what that means. So our appropriate u substitution is sine x. Derivative of sine x, folks. The derivative of sine x, is it positive or negative cosine? The derivative of sine x, positive or negative cosine? Positive, okay, good. Solve for dx, which means we're going to divide on both sides. And now when we do our substitution, we go, all right, well, what gets replaced with u now? Does the cosine get replaced with u or the sine get replaced with u? Do I mess the 2 up, or is that still there?
Still there.
So this actually becomes u squared. Is the cosine x still here?
Yes.
For right now, yes. Is the dx still here?
Yep. Or no, you
No, because
substitute.
I need to translate that into my du somehow. I know if I translate it into a u, I'm going to have a du. And I know that dx was equal to cosine x under du.
Cosines cancel.
See anything nice that happens? One of the kind of prerequisites for this to work, I told you, is you got to get rid of all the variables except for u. You can't have both x's and u's. So you have to have something that gets rid of stuff. That's why we say the derivative has to be somewhere in there, because when you solve for dx, you divide by the derivative, or you multiply in some cases by the derivative, and that will show up somehow when you make your substitution. It's got to be there. So we're going to have an integral of u squared du. Now that's a whole lot easier to look at than that, isn't it? Man, this is a piece of cake. This is going to be u to the third over 3, no problems. And then, done?
Nope.
No, not yet.
Substitute u.
Oh, you can. You can right now. Yeah, make sure you end in x's. You start in x's, you end in x's.
Plus c.
So sine cubed x over 3 plus c.
You can still write all these as 1/3 sine cubed
Sure.
x.
You can do 1/3 if you'd like. It really doesn't matter.
And that's true for all these problems?
Uh-huh. How many people feel okay with that one? Good, all right. Cool. Would you like to try a few more?
Yes.
Let's do like let's do like 4 or 5 more, then we'll talk about the area. By the way, the reason why I'm stressing this so much is because there's really only 2 sections on integrals that you covered. It was 4.1 and this. That's it. The rest of the stuff is how to use them. So it's kind of like how we did derivatives, right? We did chain rule, we did product rule, quotient rule, and then for the rest of the chapters, I showed you how to apply them. Wasn't any new different techniques, and that's the way this is going to be too. So this is the techniques you need in order to go further to solve the application problems that I'm going to show you. All right, now, how about this?
Huh. Still doesn't help though. Pull this out maybe? Forget if you can do that or not. Yeah, this is probably wrong.
You know what I see a lot? This is hilarious. I love this. This is my favorite problem. One of my favorite problems to grade, I think, because it makes me laugh and then cry. And then laugh some more when I get over crying. I love seeing that. Could you please do that for me? I see that.
Where are they?
I don't know. I don't know. Don't do that to me. Okay, that. One day, I swear, one day, I know how I'm going to die. It's going to be grading papers. And one day, my head is just going to explode. And then high velocity splatter on your paper. You're like, ah, better must have died. That's how you'll know. If I don't come into class, it's probably because you're going to kill me. People are going to kill me. No, we can't do that. Can't do that. We've talked about that a lot in this class because I need to make the distinction between an angle and a multiplication problem. So this is not true that you can just cross those things out. But what you can do is try to make that fit in an integration table by a substitution. Now, right now, it's of course not. I mean, the only thing we have that deals with cosine is cosine x. This is not cosine x. Or cosine u. This is not cosine u. We need to make it somehow that so that we can fit it. So what's the appropriate substitution? Including the cosine or not, do you think?
The square root, right?
Because if you include the cosine, well, the derivative of cosine is negative sign, right? That would have to show up somewhere in your integral. That's not there. It's also, u is typically on the inside of something. So what's on the inside of something here?
Square root x.
Square root of x.
Square root of x. Let's take that as our u. Let's see what happens. So not the cosine, just the square root of x. And the reason why we're seeing it is not here so much, it's there. That's where we're seeing it.
Now, would you substitute u?
That's a great question. That's a great question. Well, we're going to find that out right now, okay? So we made our substitution because I've taught you how to look for it, right? I said it's typically on the inside of something. So you're seeing, because I showed you that, the square root of x. Now you're going to find the derivative of the square root of x and then see what you're going to substitute for, maybe not substitute for. Do your substitution later. Later. You follow me? So let's go ahead and do this. Now in order to take a derivative, I'm probably going to write this as 1/2. Don't make the mistake of putting square or negative 1/2. That will really mess you up. You need to know how to do this correctly. That's why we spent so much time doing derivatives. So x to the 1/2. How much is du equal to? Everybody, you need to know this. What is it? Oh, great, everybody. That's like 5 people. Come on. You can do a derivative, right? 1/2 x to the what? Negative 1/2. Very good. So we're subtracting. Negative 1. What else?
dx.
Do not forget dx. Don't forget that. Okay, now we've done our derivative. What are you supposed to do now for this problem?
Solve for dx.
Okay, let's be very careful on this and solve for dx. How do you get rid of the 1/2? So I'm going to say that this is 2 du equals x to the negative 1/2 dx. Is that true for you? Just to make it seem a little bit more understandable where this stuff is going to be coming from, I'm also going to make this side prettier before I start dividing. You can divide right now, that's fine. But you could also look at it as 2 du equals
x to the-
dx over x to the 1/2. Does that make sense to you? You could divide, option number 1 is doing this way, option number 2 is this. Look at the board here real quick. If you wanted to divide right now, this would give you 2 du over x to the negative 1/2 equals dx, right? You follow me on that? On this case, I'd be multiplying by x to the 1/2 on both sides. This will give me 2x to the 1/2 du equals dx. And you know what? Look at the board.
That's what I
So
got,
that-
right? Yeah.
That one. Do you see that? Moving that negative up to the numerator will be 2x to the positive 1/2 dx, du equals dx. So there's a couple ways to do this. Either way is fine. No way is better than the other way. I really don't care how you do it. What I care about is, can you follow me? Can you guys do it from here to there and get the right signs in the right places? Raise your hand if you're okay with that. I know it's basic algebra, but you know what? That's our main struggle basically in calculus, is basic algebra. So you're okay with it? You sure? Okay. Okay. Now I'm going to answer Scott's question. Scott's question was, since I made this a u, do I make this a u?
Yeah, probably.
And the answer is, well, let's look at your substitution. You have to find a place for this, right? Do you notice how this has an x? If I make this
If you don't,
into a
you
u,
find an x.
watch what would happen. Watch. By the way, this is 2 square root of x du equals dx. You guys see that, right? Look what would happen. If I do cosine u over u, cosine u over u, I can't just make this a du. Even if I did, it wouldn't work because we don't have cosine u over u. That doesn't work. You can't make it u to the negative 1 times cosine u and split it up. So you don't even know how to take u to the negative 1 because it's ln u. We're not even in that part of the class. So we can't do that one anyway. But this would not be du. It would be 2 root x du. Is there a place to get rid of the x? What's the one necessity for substitution to work?
Gotta get rid of dx.
You've got to have just u's, right? Just u's, and it has to fit your integration table. Otherwise, you
So-
did something wrong, or you haven't gone far enough. Now, we did something wrong because we can't cross that out, and that's a problem. If you have 2 different variables, that's typically a big problem for you. You've done a mistake in the previous problem. Now, what I can tell you is this. This was the correct substitution, right? dx was that. So that's the correct substitution. I know that I picked my u here, and that's the inside of something, so that had to be right. The only wrong part was probably this one. And if I move it back to what it actually is, the square root of x, do you see how that's really going to help us out? What's that going to do for us? Mm-hmm. So that's gone. Hey, now I'm good to go. By the way, that 2, is that a 1/2 or a 2 over 1, what is that?
2 over 1.
So when I pull this out in front of my integral, it's 2 cosine u du. Oh, that's a pretty easy integral right there. That's a pretty easy one. What's the integral of cosine u du?
Oh wait, I forgot to substitute.
Positive or negative sign?
Positive.
Very good, you get the hang of it. So sine u, this equals 2 sine u. That is 2 sine, let's go ahead and substitute back in for what u is. Put like the square root of x. Put a plus c behind it, and you are done. We still feeling okay? Okay.
Wait, is it not negative? Oh, I was looking at derivatives.
Tell you what I'm going to do. I'm going to give you one to do on your own. We'll kind of go back and forth like that, hopefully for a little while. I'll give you one, and maybe I'll help you with the next one, but I want you to mostly do it. Let's see if you can manage to do this one. Go ahead and follow the process down of finding a u. It looks horrible. It's going to look horrible. It's not going to be horrible though, as long as if you follow this process. There you go.
Oh, it does look pretty bad. Wait, this one might be easy. What's going on? I cannot, right? Wait. maybe.
Hmm?
Really?
It looks bad, doesn't it?
Yeah. Only a little.
It's not bad. It really isn't. The hardest ones are trig ones. Manipulating trig identities to get something that fits your integration table, that's the hardest. For us, it's either, I mean, if it's not trig, it's a finite integration table. It has to fit. So if it doesn't fit directly by breaking up fractions and combining like terms or something, or separating integrals, then it has to fit with a substitution. If it's not those two things, it's not going to be in here, or we can't do it. Why don't you give it a try? I want you to find your u. I'll put the u up on the board here in just a second. Take the derivative of both sides, do your substitution, and see what happens. Remember, it's up to you to find your u. You guys got to be able to do that. I can't just walk you through it all the time. When I pick my u, should I pick it with the cube root or without the cube root?
Out, probably.
Definitely without. Definitely without. With the cube root, it's a chain rule. Very hard to do. You have some crazy stuff going on. Definitely without. Did you pick that as your u? It's inside something. The derivative is kind of up there. Not really because we have the constant, but kind of up there. It's good. Good sign. Derivative. Oh, man. 25x to the fourth or negative 25x to the fourth? Better not lose that negative. Oh, goodness. Let's do a little dividing.
Look at
Now
that.
we're going to go real slow. This is not the time to take it quick and make a mistake by doing the math in your head. It's time to write it out and really get the handle of this stuff, all right? Not doing
yeah.
everything all fancy-dancy. I know there's an x to the fourth. I'm going to leave it a cube root for right now. I'm going to make it a u in there. Did you make it that far?
Yep.
Wait, not even if you did. You actually made it that far. Yes, these two rows, yes? The dx. The dx is du over negative 25x to the fourth.
X to the fourth
Right
cancel.
here, you should be able to tell whether you made the correct substitution or not. Don't hammer at this thing if you made the wrong substitution. Should be apparent to you. Did you make the right substitution? Yeah, how do you know? That's great. That's what you want to have happen. So x's are gone. If that happens, most likely you made the right choice. Are there times when you didn't? There's times when you have to go further, yeah. But for us, most of the time, this works nice. Okay, let's make things a little bit better. Tell me what I do with the negative 25.
Take it out.
And it becomes what?
1 over negative 4.
Negative something, right? Negative 1/25, whatever that is, I don't really care. How about the cube root of u? Is it u to the third, u to the 1/2? What is that?
U to the third.
U to the 1/3, very good. And then du. We made our substitution, no problem. We kept it a cube root, okay. We kept x to the fourth, we don't change that yet. We made our dx exactly what we solved for, not a big deal. Crossed out our x to the fourth, that's great. Pulled out the 1 over negative 25, made negative 1/25, perfect. We have a cube root into a 1/3 power, and now we have something that fits our integration table. And it looked nasty, easy. That's easy. Has to be easy. Has to fit your integration table. If it's not easy, you did something wrong. It's not necessarily true. Some of them kind of get a little bit nastier, but for the most part, that's true. Oops. Oh, by the way, this is a good time to tell you this. When you do an integral, you don't write the integral anymore. So I'm not going to do this. I'm not going to write u to the, what is 1 plus that?
4/3.
4/3 over 4/3.
Over 3/4.
Yeah.
Or the 4/3.
Like that.
Equal by its half.
You don't keep writing the integral. It's like taking a square root of something, right? If you do this and you take the square root of 49, you don't write the square root of 7. At least I hope you don't write that. You just write 7. Right? When you're done with the square root, you're done with the square root. When you're done with the integral, you're done with the integral. You don't keep writing it. Just like a derivative, you want to keep writing a derivative. Now let's make this side a little bit better. We got -1 over 25. We have 3u to the 4/3 over 4. Do you see how to flip that up?
Mm-hmm.
We can do 3/4 times u.
You could. So we're going to go ahead and multiply that. That's going to be -3u to the 4/3 over, looks like 102.
That's what I got so far.
Plus C, we don't have to do it quite
Yeah,
yet.
we need
If
to
you want to, that's
substitute.
fine. Just make sure you have it at the end of your problem, all right? So right now, there's one more thing I need even before plus C if you want. Yeah, we don't want to end in U.
So I think I'm good with the substitution problems that don't have trig functions in them.
What you can do, you can go one more step on this thing and put it back into radical notation if you would like. That will be -3 a cube root 3 minus 5x to the 5th all to the 4th power all over 100.
I guess. I don't think I did that. No.
Plus C. I was waiting for it.
Yeah.
Waiting for it. Plus C.
Or -3.
Yes, no? Yeah, you could have the -3 over 100 times that whole thing. What I really care about is, do you see, I mean, when you get really good at derivatives, you've been doing this for a while, you can see it even better, but do you see that this is the derivative of that? You see some things coming out of that? 4/3 goes down to 1/3. Derivative of the inside is something x to the 4th, there's just something x to the 4th. That 25, it's gonna simplify down to that. So that is gonna work. It's a nice way to kind of check your work is with the derivative. You having fun yet?
Yeah.
This is like the pure non-theory part of this class, right? It's just like we're just hammering down on some problems right now, which I guess can be kind of fun. We get theory part probably next time, where we're going to find out why this is the way that it is. Because I said so.
That's your theory behind everything? Yeah. 3 ways to do things, right way and wrong way and too much way.
So there's a way how they discovered the term for the right way, all right?
Will this be 1? I don't know about this. If I substituted x squared. Does that help? Yeah. Well, this kind of sucks. What is this? Maybe just x? Because you're gonna get the same thing anyway. U squared u minus 1 du. Well, there's no x's now. Interesting. U minus u. Okay, something is not right here. What? Alright, let's see.
So integral of x squared square root of x minus 1. Now this one might trick you if you really don't
It's a
listen to
tough
what I've said before. This one might trick you. Here's why it might trick you. I said two things have to happen. First, you pick your u so it makes it easier. You pick your u because it's typically the inside of something, and you pick your u where the derivative is there. That's where the problem might come in here.
There's no derivative?
Because, and it goes in the order which I told you. It goes in the order of pick it, make it easier, pick it, make it on the inside of something, pick it so the derivative is there. Now, is this on the inside of something? The derivative is not really there, because that's the inside of something. That's a problem. Now, if I pick this as my u, my derivative is just 1. That doesn't take care of the x squared. So this is kind of something where like, oh my gosh, I have no idea. Pick something. Pick something. And pick something that's the inside. That's the best way to start. If you pick the inside, do you notice how you don't know how to take the integral of the square root of x minus 1, right? But you do know how to take the integral of square root of u. You with me on that? If it's u to the 1/2, that fits. That's how you pick your u. So here you go. All right. Let's go ahead and pick our u x minus 1. Are you okay with this so far? All right. Du is what? 1 dx.
Yeah, and then from here, no idea.
Or in other words, simply dx. Feel okay? You sure? Now, we're going to do some fancy math. Fancy math. Is x squared still there? Is the square root still there? Is the x minus 1 still there? What is it? It is me. And is the dx still there? Is du. What's the problem on
Still
our
x.
problem?
We have x's and u's.
Yeah, you know what's not cool about integrals is you can't pull out like an x squared. That just doesn't work, right? Because otherwise these problems will be very, very easy. Otherwise you can just separate them here and that would be nice, but you can't. You have to make everything either all x's and work or u's and work. The problem is, this is our problem, that x squared right there. This is nice, that's great. That's our problem. How do we deal with our problem? Well, maybe you see it. Do you see anything we can do? We could kind of maybe manipulate the substitution we have to fit that. So for instance, look at our substitution. It's u equals x minus 1. You follow? Here's the logic here. I hope you can follow this.
Wait. U plus 1 squared. Oh, I didn't think about that. Because you can rewrite this as u plus 1 equals x. U plus 1 squared square root of u du. U squared plus 2u plus 1 square root of u du. U plus 2 square root of 2u plus square root of u, maybe. I'm not too sure about that.
The logic is, what if I can somehow make another substitution for x squared? If I can do that, maybe it'll work. I don't know. Like we're trying here, but maybe we can do that. So look up here at our board. We got u equals x minus 1. What I want you to do, whenever you get this case, and you know you made the only substitution you can make, right? That's the only one you can make. That's it. No other substitution will be even close to good. You know you made the only one. Try to do another form of substitution over here. So for instance, I want to get an x squared. Let's make this somehow an x squared. Tell me what I have to do.
Oh, make it an x squared? I didn't think about that. Wait a minute. It's gonna end up being the same thing. U plus 1 squared. Oh, and I got rid of everything. And before I do anything else, I'm gonna make sure I'm right.
Probably solve for x first would be a great idea. Let's add 1. If you add 1, do you see that you get x equals u plus 1? Follow me on that? X equals u plus 1. How do you get x squared out of x?
Square both sides.
That is an equation, isn't it? If I square both sides. Yeah, that works. That works. You okay with that one? Note that if you distribute this, you get u squared plus 2u plus 1. You still okay?
Should be distributed.
Yes. Notice there's no dx, there's no du, there's nothing because we haven't done derivatives here. All we're doing is making a direct statement of what x squared is in terms of u. And we got that from our substitution. By show of hands, how many feel okay with what we've just done? Have I lost you at all?
Nope.
No, we're okay, okay. Let's see what we have. Instead of x squared, I've already solved for x squared. I've got u squared plus 2u plus 1. What must, absolutely must. Why? Because we have multiplication. And you got square root of u. Probably a great thing to do at this point would be change that into an exponent. U squared plus 2u plus 1 times u to the 1/2 power du. Now, why did I do that?
It's easier to think
Why,
of.
why is this going to work for
And
us?
be
What can you
distributing
do? If you distribute, everything's in terms of u's, right? Can't you use those exponents to your advantage? No, notice what we can't do. We can't just take an integral right here. We can't take an integral right now. We would have to absolutely distribute that. So when we do, recall that you add exponents when you multiply. So this is going to be u to the 5/2. This will be 2u to the 3/2 plus u to the 1/2 du. Did I do my math right on that? Can you take an integral of that one? Very easily. Each one of those fits. Remember, we're going to start.
Oh wait, you do have to add them because you're not distributing just an exponent. Okay, never mind. Forgot about that rule. Guess if something's attached to the exponent, then you have to add it, not distribute it. Wait, you did the 1/2 at the end? Really? Oh wait, that's a 1. Oh yeah. No, I just said that in my head. Got it wrong. So 1. This is a u to the 1/2. Okay. du. Cool. did a lot of that in my head, so it could be wrong.
Stop writing our integral.
Oh, and then, well, I'll substitute once I see if I'm right or not.
If we manipulate those fractions, what I'm looking at is 2u to the 7/2 over 7 plus 4. Notice the 2 times 2. U to the 5/2 over 5 plus 2u to the 3/2 over 3. We're very close to done. What's the last thing we got to do?
Substitute back.
Yeah, we got to make sure we're in terms of x, not u. Put a plus c at the end, and we will be done. So final answer. What was it? X minus 1? Now you can make those all roots if you'd like to. They're all square roots of x minus 1 to some power. You can leave them as fractions. I really don't care. As long as you make that far, that's great. That's what I care about. How many people feel they can make it that far? Good. Now we have a couple more minutes. So let me show you one more example. We'll finish this off next time, but I want to just talk about the first step. What's a good choice for your u? Is it?
Probably the inside here of the square root. And it looks like set up for a derivative, so since it's a polynomial. X minus 8. Right now, my own. dx. I was going to autopilot there. Four x minus 8 square root of u. Du over 4x minus 8. Factor out its 2. Or no, 4. 2, wait, x. Dang it. It looks so close, but it's x minus 2, not 2 minus x. That really sucks. Hold on. No, dang it. This one does suck. Maybe I'll have to move around the U again. equals this. I don't know.
Is it 2 minus x? Is it including the square root? Is it the 2x squared minus 8x plus 1? Probably. If it's going to be anything, it's probably that. You don't want to pick just a little piece of that. If you're going to pick something, pick the whole thing inside, right? Not the whole thing include the square root, but the whole inside part for sure. If we were to pick that, which is really, if you can see it, if you kind of get an understanding of this substitution thing, that really is your only even close to good choice here. You with me? Now the problem is, if I pick u for this, is my derivative of this up there? What is my derivative?
4x minus
4x. dx like that, right? Make sure you have parentheses around that. My question is this: can you make this thing look like this thing?
Almost.
Factor out not a 4, not a 4.
Wait. Negative 4? Wait, yeah, negative 4. Or plus 2. Okay, I see. And then the negative 1/4 would just come out. U is this whole thing.
If you factor out a 4, please watch. If you factor out a 4, you get x minus 2. Does that match up? No, those are not the same. Negative 4. Oh, negative 4. But factor out negative 4, negative, positive, or in other words, that. Does that match up? Now that's great. That's what you want to have happen. So the reason why I give you these last 4 examples is to show you that your U might still work, even though it's not maybe completely obvious to you. You need to think through it. You might have to manipulate just little pieces of it, and then it works perfect. Remember, it has to work perfect. Otherwise, you can't do a substitution. So somehow manipulate it. Work with it. Don't just give up on it. Also, we'll finish this one off next time, and 2 more. So we're going to continue finishing up this problem. What we're seeing is how to do substitution, even when it doesn't look like maybe you can do a substitution. Sometimes you can. So all you got to do is just try it out. Now, last time I believe we were talking about picking. This is our U, and seeing if the substitution will work. When you pick your substitution, again, it has to be on the inside of something, and typically everything, as far as the derivative goes, must also be in your integral, disregarding the constants. So here we're going to have a du equals 4x minus 8 dx. We all know how to do that. The problem is that's not directly in your integral. So you're going to have to manipulate it at least somehow in order to make this thing work. Now, one thing people suggested was, what if we were to factor out the 4? If we factor out the 4, you got x minus 2. dx. That looks pretty close, but it's not exactly right, and it's got to be exactly right for you to eliminate it. You follow me? So what was the suggestion someone else gave after this? Maybe instead of 4, yeah, then negative 4, because what the negative 4 would do, factor negative 4 out, changes that to a negative and that to a plus. And if I just reorder it a little bit, I get 2 minus x dx. So far, so good? Of course, we can solve for dx. And now we're finally ready to do our substitution. If we do the substitution here, we'll get, do we still have a 2 minus x on the numerator? You still have a 2 minus x on the numerator.
Yeah.
That's not something we've gotten rid of yet. Remember, the only things you can get rid of is whatever you're calling your u and whatever you've solved for dx. That's the only 2 things you really substitute in for. Everything else should take care of itself, really. So here we haven't touched that yet. That's 2 minus x. The square root, should the square root still be there?
Yeah.
What's inside of the square root? That was our entire u. You're right. And then should dx still be there?
No.
Yeah.
dx?
No.
We'll make that substitution, that nice jump. It's also nice that we made it look exactly the same here. That way it's very easy to see what we can and what we can't do with our problem now. So what can you do? That's completely gone. What do you do with the negative 4?
Move it outside the 1 over negative 4.
Okay, so I'm going to make it negative 1/4 if that's okay with you guys. What else would you like to do?
Turn your square root of u into a negative u to the negative 1/2.
Okay, so the square root itself turns into a 1/2, but then to move it to the numerator, that's where it becomes negative. So yeah, you're absolutely right. We're going to make this negative 1/4. We haven't done anything with that. Integral of, that's u to the negative 1/2 du. From here, it fits our table perfectly. That's great, because if it didn't, we'd have to do more work. We don't want to do more work. Make it as easy as possible, then do your integral, then re-substitute back in from u back into terms of x, and you're done. So in our case, we've got the negative 1/4 still hanging on. We've got u to the, what's that going to be?
1/2.
Over? Over 1/2, yeah. Exponent over new exponent. Still okay? You sure? This 1/4 and that 1/2, notice that really this 2 is going to go up to that numerator, because you separate, reciprocate, and multiply. You'd get, I'll show you both steps here. You'd get negative 1/4 times 2u to the 1/2, like that. Well, this is going to simplify. Negative 1/2 u to the 1/2. Or you could have it u to the 1/2 over 2. Negative u to the 1/2 over 2, that's fine. What we got to do now is what? Yeah. So I'll make it negative 1/2. U becomes whatever we had for our substitution. That's 2x squared minus 8x plus 1 to the 1/2 power. What's the 1/2 power again?
Square root.
So could you write this as a square root instead of that 1/2? Sure you could, that's fine. Plus c. Show of hands, how many will be okay with this so far? Are you getting the hang of the substitution? Hopefully after the practice last night, that you had at least a great idea of what's going on. The last one we're going to talk about is this one. I'll give you one more trig one because I know you guys love it so much, right?
Oh, yeah. Woo, thank you.
You're welcome. That's a good one. Why is that a good one? Because right now you're looking at it and you're stumped, right? Because I would be, if I was in your seat. I wouldn't know what to do.
It's the derivative of cos x, negative sin x. This probably isn't gonna help. This isn't a constant, so yeah, I don't know.
We could try some things. You could try picking x. That's not really going to help, right? Just changes cosine cubed of x to cosine cubed of u to u. That doesn't really do much. We could try picking cosine x, right? Because that's cosine x to the 3rd power, true?
Yeah.
But the derivative of cosine x is sine x. Is there sine x up there? Then that would be a problem. Whenever you come around this situation, you know that the derivative of cosine is basically sine, negative, but basically sine if you ignore the constant, and the derivative of sine is cosine, right? You're going to have both those things up there. So when we have a cosine cubed and there's no sine, that's going to be really hard to deal with if we don't have a sine, because as soon as you pick some u that has a trig, you're going to have a derivative that has some trig in it, right? It's got to be up there somewhere. Here's maybe a way to deal with this.
Yeah, I don't know.
Break off something that you know has an identity to it. For instance, cosine cubed, I don't know any identity with that.
Cos
But I
squared.
do know an identity with cosine squared. Maybe break off a cosine squared, see what happens. Isn't the cosine squared going to give you a sine squared in there somewhere?
Yeah.
We'll see. We'll see what happens. that was relatively painless. Cosine squared times cosine is still cosine cubed, so that works. Now, I still can't pick that as a u because the derivative of cosine is not cosine. So I got to change this into a sine somehow, and then we'll take our u. How much is cosine squared? Cosine, there's no identity with that, right? But cosine squared has an identity. What is cosine squared? Very good. You use the Pythagorean theorem, the Pythagorean identity for sine and cosine, I mean. And what this says is that instead of cosine squared, sure, why don't you make it 1 minus sine squared x? Which is true because if sine squared x plus cosine squared x equals 1, subtract one or the other and you have the alternate trig function that you're looking for. Do you feel okay so far? Now let's think about this. Think about it. What should your u be? What should your u?
1 minus sine squared x? No. Wait, yeah. Hold on. If it's cos x, it's going to end up being negative sine x. That wouldn't get rid of this. Because there's this 1 is attached to it. If you took this, then what's going to be cos? Let me try that. Still don't know.
B.
It'll be a positive sign because negative 1 should get 1 minus sign.
Are you saying, wait, I'll give you options. Your only there's 4 options. 2 of them are not good options. Option number 1 is 5 options, I guess. Wow, you can really screw this thing up. Option number 1 is picking x for u.
No.
Not going to do anything. Option number 2 is picking cosine x for u. This is going to hurt you with that, right? Because you can't directly just cross out that sign. You can't do that. And you still have a sine x there. Still have a sine x. That would be a problem. Do you see the problem? Bad option. Option number 3, picking the whole entire thing here. Picking the whole entire thing. You pick the whole entire thing, you got to take the derivative of the whole entire thing and it has to show up. Derivative of the whole entire thing is a general power rule. See general power rule there? 2 sine x cosine x. Does that appear? No. Bad option. Option number 4, picking just this part, sine squared x. Is that a good option? Again, you have to take the derivative of that. That's 2 sine x cosine x. That's not up here. Again, you pick the inside thing. Remember that this is sine x squared, right? You with me? This is this.
So just sine x. Okay, let's see.
the u's are inside of something. You rarely take a u that has a function and a power. That's too much. Because when you take the derivative, it's a chain rule. If you're having to take a chain rule for your derivative of u, you might have picked the wrong u. You see what I'm talking about? Because you're going to get that function back again, and it has to appear exactly in your integral. That's oftentimes not going to happen. So this whole thing, no, because that's a chain rule, or general power rule, however you want to say it. This thing, that's the inside, is the derivative of sine x in your integral. Then that's the correct u. What is the derivative of sine x? Is it positive or negative cosine?
Positive.
I still have some people giving me negatives. Be careful on what you're doing. Integrals versus derivatives. This is a derivative. Derivative of sine x is positive cosine x dx. When you divide by cosine, you get du over cosine x equals dx. Hey, we're almost good to go. Let's check this thing out. We've got an integral of 1 minus... What's the sine x going to become for us, folks?
Sine squared. Or no, hold on. Okay, said u.
Did we sell
U
a
squared.
square? Yes. So you didn't even have to deal with the square, right? U squared is easy. You didn't have to pick the whole thing because you can take an integral of u squared. That's great. Do I still have a cosine x right here?
At this point, yes.
At this point, absolutely I do. Do I still have a dx? It is, instead, our substitution is du over cosine x. Does something nice happen? Nice, awesome. Now, I do know it's easier when I do it than when you do it at home, right? You probably spend 20 minutes on that problem, which is okay, but you're going to start learning some of these things as you go on. I think I gave you some hints at the beginning of the problem. When you have trig functions, the derivative has to be there, so break up some things. See if you can make it. See if you can work with it. This one's turned out to be so nice. 1 minus u squared du. That's not bad. Not bad at all. Okay, take the integral of 1 minus u squared du. Fits perfectly in our integration table. What's the integral of 1? Tell me that. X?
U.
No, not x. U. U? Yes. Why u and not
Respect
x?
to u.
Because
Look at your variable you're integrating with respect to. That's why the d whatever is important. U minus what?
2u.
Not u.
No.
Bruh.
And then 1.
Don't get confused. I know it's confusing. You're going between derivatives and integrals, and we're doing them in the same problem, right? Derivative of sine, and then you're going to take integral of... Oh, man. Be careful. Don't rush. Just think through it. So far, okay?
If we're done pretending here, we gotta add plus c.
At the end.
Substitute.
You can add it here. I don't care. Substitute in? Yes. So u was right here, sine x. Sine cubed x over 3 plus, that's what you need. Do you feel okay with it? It's going to take a while to master it, right?
Yes.
Practice, a lot of practice. But it's possible. You know, you guys have the fundamentals down. You understand the substitution. That's really all there is to it. As far as substitution goes, the substitution part's pretty easy, right? It's making it fit the substitution that's a little bit harder sometimes. But work with it, especially the trig ones, get through that stuff, get over the hump, and then you'll be okay with it. This is the last example as far as substitution I'm going to give you. Are there any questions before we move on? All right. So now that we've basically mastered how to take an antiderivative, find an antiderivative, we have fit in the table, which is in the problem, just undoing a derivative, and we now have integration by substitution, which does the same thing, just a kind of fancy way to do it. We're going to find out why all this stuff actually works. So we're going to study in section 4.3 how to find the area. How to actually find the area. Now, we've done this. I've told you that it is, that integral is basically finding the area. But would you like to see why? I hope you want to see why. This is the why part. So here's the why. Because I said so. No, it's, I wish. Make my job easy. Do it because I said so. Let's talk about area as a limit. Before we can get to area as a limit, I gotta tell you something about what's called sigma notation. You ever seen a sigma before? If you're ever in a fraternity or something, you know there's these Greek letters called sigma. Sigma is this, looks like a sideways capital M. Looks like that. You seen those? What's it mean? Yeah, it's a Greek letter S, really, so it means sum. It says what you're supposed to do is add whatever I tell you to add. So let's just give a quick, easy example. That right there, that k equals 0 says the variable, or the indices I'm going to be using is the letter k. I'm going to start where k equals 0. I'm going to stop where k equals 5. And I'm going to do that to each of the following. K cubes. Here's what sigma notation means. It says what you're going to do is let k go to all the integers. Integers are the whole numbers between this one and this one. So basically between and including. So you're going to start at 0 for k, then you're going to go 1, 2, 3, 4, 5, and 6, right? Why not 6? That's too far. That's too far. So we stop at 5, and we're going to add all of that up. So sigma notation says it's a sum. Sum means add. You'd have 0 cubed, plus because you have a sigma. Then you'd have, oh, the next one is 1 cubed. And then, oh, okay, we're going to add as a sigma. Then we'd have 2 cubed, we'd have 3 cubed, we'd have 4 cubed, and we would have 5 cubed. And that's what the sigma notation actually stands for. Do you feel okay with the sigma notation? So, k cubes. Here's what sigma notation means. It says what you're going to do is let k go to all the integers. Integers are the whole numbers between this one and this one. So basically between and including. So you're going to start at 0 for k, then you're going to go 1, 2, 3, 4, 5, and 6, right? Why not 6? That's too far. That's too far. So we stop at 5, and we're going to add all of that up. So sigma notation says it's a sum. Sum means add. You'd have 0 cubed, plus because you have a sigma. Then you'd have, oh, the next one is 1 cubed. And then, oh, okay, we're going to add as a sigma. Then we'd have 2 cubed, we'd have 3 cubed, we'd have 4 cubed, and we would have 5 cubed. And that's what the sigma notation actually stands for. Do you feel okay with the sigma notation?
Yep.
I need a head nod before we go on any further. You okay with that one? Okay, good. Well, whew, scared me for a second. Now, do I care what that is? Yeah, ultimately I do, but I'm going to give you better ways to manipulate that. Before I give you those ways, I got to tell you about some properties. They're not hard properties. In fact, you're going to discover that they're very, very similar to what we can do with derivatives and integrals, namely these two. If you have any summation oops, I missed something. And you have a function of k, that's a function of k, right? Times a constant. What you can do is this.
Pull out the
That
constant.
c, if it doesn't depend on the k, you can pull out in front of your summation. That's a true statement. You can pull out any constant. So this would be if C does not depend on K.
Only in terms of multiplication.
Yes. If C does not depend on K. Let me show you an example. This is going to blow your mind like a grenade, like a mind grenade. Some of you are mind like a grenade, like a mind grenade. Some of you aren't going to like this very much till you really think about it. Hopefully you think about it, that way you like it. That's my circular logic for you. What's your indices, your index? No, your index should be the letter that starts at 1 and goes to 5. J is your index here. So the function should be in terms of J. Anything depending on J cannot be moved outside. Anything not depending on J for this context is like a constant. What's the
Okay.
function inside? X to the third, right? Is that a J?
No.
Has nothing to do with J, right? Nothing at all. You know what I can do with that? This does not mean the same thing as this does. This is not that right here. This is x cubed. X cubed. If I had this, if I had x cubed times j, then this would be x cubed times summation j equals 1 to 5 of j. I could do that. Anything not depending on j that's being multiplied, I can take out. Believe me? Now I'm going to erase this because I want you to really think about what this means when I have no j. When I have no j, what's there?
Wouldn't it just be x cubed? It's like a 0. Or wait, no. A 1? J equals 1?
Oh, what? You were right, I just didn't hear you. That didn't make sense. Yeah, 1. Very funny. What does it mean to do a summation from j equals 1 to 5 of 1? I need you to kind of get that, where you have a
It's
constant
just
inside.
always 1.
Here's what this actually means.